It was missing, and someone brought another one. So.
Oh, okay.
Yeah. So that's a laptop.
Yeah.
Sure.
I guess we can start, right?
Yeah.
Okay, hi everyone, thanks for coming. This next session is about collaborative filtering microservices on Spark with our guests here, Rui, Vieira, and Sophie Watson. Okay, thanks.
Okay, so hi everyone. My name is Rui, and I'll be talking today with Sophie Watson a bit about collaborative filtering in general, and specifically how to implement a recommendation engine using a microservice-oriented architecture on top of Apache Spark and OpenShift. So we'll talk a little bit about collaborative filtering. What is collaborative filtering? What is a recommendation engine, basically? How to implement this on Apache Spark. We'll go a little bit about Apache Spark. We'll talk about one of the most popular implementations of recommendation engines, which is ALS, or alternating least squares. And we'll also look at how we decided to implement this as a microservice-based system. And in the end, we'll look at some of the problems which we found, some of the solutions that we came up with, and some takeaway messages also from this type of problems. So first of all, collaborative filtering is a very popular way of implementing recommendation engines. But the fundamental question is then, what is a recommendation engine? So a recommendation engine is just a way, or an algorithm or a method, to try to find affinity between a pair of users and products. So fundamentally, that's all there is. And there are several ways to implement this. So you have recommendation engines which are based on content systems, recommendation engines based on knowledge systems, but we'll focus just on one specific method, which is collaborative filtering, in specific the implementation of ALS. So collaborative filtering is just an umbrella term for a family of algorithms which try to, as I said, try to find this affinity between a pair of users and products and a strength of that affinity, so a rating. So it might seem that if you look at collaborative filtering, it might seem a bit like common sense, because the main idea behind it is that if you have a group of people that share common interests or common tastes, then if they have a similar taste on a lot of products or on a lot of items, then it's probable that you're going to have the same feeling as them or the same taste of them. So this feels like common sense, right? And one of the characteristics of collaborative filtering is that this method is user and product agnostic. So it means you just try to find the affinity between three numbers, so a user ID, a product ID, and a rating. So in the end, you can just use the same methods and the same algorithms for a whole myriad of cases. So you can be trying to find or implement a recommendation engine for cars, for books, for movies, for music, for likes on social posts, social media posts, or even for software packages that people install. So how does ALS work, or collaborative filtering? So collaborative filtering has a very popular implementation on ALS, which is alternating least squares method. And the main motivation behind it is that if you can arrange the ratings in a matrix form, so if you have a sequential ordering of users and products in such a way that you have a column for each user and a row for each product, then you're going to try to factorize this matrix and try to find two separate matrices called usually U and P, which are latent factors. And those latent factors, when multiplied together, will give you an approximation of the original matrix. So as you can see here, so after having this process of factorization of the matrix, then you can just get an individual rating. And if that original matrix of the ratings has high sparsity, that means not all of the users rated all of the products, then the resulting approximation will have all the entries filled, and you can get one of those approximations as the prediction of your rating. So after you have that factorization, then, as I said, the final approximation matrix will be just the prediction that you want. So how do you do this? Well, basically, we can just devise a loss function, and that loss function can be minimized. Unfortunately, in this case, we have a closed-form solution for the minimization. That means that it just reduces to a problem of solving linear equations, and we're going to solve that by iterating for both factors, having one estimator. We try to solve for one of the latent factors, then we fix the other one, then we alternate. We fix the original factor, and we solve for the other factor. And we repeat this product until the two latent factors converge, or until we have an error measure which is small enough that we can say, well, okay, this is a good enough approximation. We're going to keep these two latent factors. So in modern software development, so we have more than one person working on a project, right? We all know that. And one of the advantages is that we're going to have, since we're going to have an heterogeneous team, we can try to divide such a system as a recommender engine on a set of microservice-based oriented system, which means we're going to have specific services which are going to be oriented for a single task. And in that way, I mean, we have several advantages. So one of them is that we might have people that are going to work on an area of their expertise. So for instance, we might have data scientists working on the machine learning parts of our system, so they can be working on a modeler, they can be working on the predictor, and we can have, for instance, user experience or UI people working on the front end. We might have software engineers, data architects working on other bits like the back-end storage, etc. So we can leverage the ability of each people on the team on each service separately. So these are as other obvious advantages. So one of them is that if we keep the communication API stable between the different services, this means that we can actually do some refactoring, internal refactoring on each of the services without impacting the rest of the services. And also, you can speed up the development cycle. So for instance, we can create mock services, so we don't have like people depending on some of the other services which are not implemented. So just an example, if we don't have a predictor ready, we can just have like a mock predictor which can just make up some predictions, and then everyone can just happily keep on working on the front end, etc. So you can really speed up the development cycle. So we can also redeploy this with minimal disruption, and that will also help quicken the development cycle of our recommender system. And operational tasks can be simplified as well. So for instance, if you want to do monitoring or benchmarking on each of the separate services, we can do it very easily. So we can just have people focusing on the storage backend, or we can have people just measuring how good our predictor is, doing some testing, doing some A/B testing, etc. So it really makes sense to implement such a complex system in a microservice-oriented way. So in the specific case of this recommender engine that we've tried to implement, we had precisely that. So we had different people working on different aspects, on different services, and we also had the chance of working on a polyglot environment, which means that each person could have the freedom of choosing their own personal taste of development or whatever tool it makes sense for the task. So in this concrete example, we've used an array of languages and technologies underlying. So for instance, we had three main areas on this recommender system. We had the front-end user-facing component, which would be the front end. We had the storage components, which would be the data store and the model store and the cache store. And we have the machine learning specific bits. And common to these last two services on the bottom, so the modeler and the predictor, they would be the only ones which would be using a Spark cluster. So they'd be sharing a Spark cluster to do all the machine learning tasks, such as the prediction, such as the model training, and also the testing of diagnostics of the model. So now Sophie is going to talk a little bit about one of the components, the model where it was actually implemented, and some of the tasks that she faced when trying to tune it for recommendation engines.
So if you haven't come across it before, Apache Spark is a fast and general engine for large-scale data processing. You can use Spark interactively from the Python, Scala, or R shells. And for the purpose of what I'm going to talk about today, we're going to be using Python, but feel free to swap out Python for a different language when you implement this yourself. So in Python, we've got this PySpark MLlib recommendation module, and within that, we've got an ALS class that meets all of our ALS needs. So I want to talk to you about the two services that are built on the Spark cluster, that is the modeler and the predictor. Okay, so the modeler is the function that takes in the original ratings matrix R and returns those two-factor matrices U and P. So those two-factor matrices are of lower dimension, they're smaller for us to store, and they allow us to easily cover the prediction. We'll come back to covering the prediction later. Within Spark, we've got this, within Python, within the ALS class, we've got this train function. So the train function takes in the ratings matrix in the form of the RDD, resilient distributed data set, along with some other tuning parameters, and it spits out our two matrices, U and P. So the tuning parameters of the model are the rank, which is perhaps the most important, and the one I want to talk a bit more about. So the rank is how many features we have in these matrices that we're decomposing our original matrix R into. So you can see that if we had P items and N users, then in this example our rank is K. So one of the other parameters is iterations. So we mentioned that in order to get our matrices U and P, we have to do some optimization. And the way that that's done is first by fixing U, optimizing for P, and then fixing P, optimizing for U. And that process is repeated. The more that's repeated, the better the results we get. But there's a time cost involved with that. So we'll talk about that a bit later. The final parameter is Lambda, and Lambda just prevents overfitting of the model. So any sort of model building procedure will have that. Okay, so that's great. We now know how to use the train function to take from our ratings matrix R into our two-factor matrices. But how do we get predictions? Well, luckily for us, also living in that ALS class, we've got this predict all function. So the predict all function takes in an RDD of user product pairs and the output from the ALS train function and model, and it returns you a prediction. Okay, so let's have a little look at that on a real data set. So the data we're using is the Movie Lens data set. So this data was collected as part of the Group Lens project at the University of Minnesota. It's widely used in recommendation engine research. So there's two data sets. There's a small one, 100,000 ratings. That's great for initial investigation and development purposes. And then there's a large data set that's good for building a more robust model. initially, I've decided I'm just going to say what do I think about the first 10 films in the list. So in that first line, I'm creating my user film pairs and putting those into an RDD. In the second line, I'm predicting, and in the third, we're doing a little bit of Spark manipulation to add some useful information, i.e. the name of the film. So what we're seeing here is the film's ID, the rating predicted for me, and film's name. Okay. So I want to talk a little bit about the tuning that we do. So I mentioned the parameters. So let's just have a quick look at our tuning method. So what we're doing is we're splitting our data into a standard training and validation set. So the training set I've taken to be a random 60% of that original ratings database. I built models on that at fixed parameter values and then evaluate it using a validation set. So I took the ratings that were in that validation set and see how good are they compared to what we, how do they compare with what our model gave out as a prediction. And then we tune for the parameters. We also do error for validation. So what you can see here is just what happens when we remember rank. So remember that was the number of features and root mean squared error. Oh gosh. Okay. And in over here we see lambda. So we pick a rank of 8 and a lambda of 1. Okay. And finally, iterations. So the more you iterate, the better your results become. But you wouldn't want to iterate forever because that would take longer. So what we do is we just implement a basic stopping rule. You say if the root mean squared error times t is within 1,000, if the root mean squared error times t plus 1, we stop. Okay, so I'll pass back to Vieira to talk us. Oh, iteratively. Okay, so that was about how we initialize the parameters. But we are also keeping an eye on the data store to see if any new ratings have been added. And if they are, we retune and we do a bit of A/B testing for the model to check that the parameters are still okay.
Okay, so thank you, Sophie. So now let's just look a bit at the other services. So one of the services that I've mentioned sorry, were the data store and the general stores. So the data store in this case was implemented as a Postgres database, and its main role was to store the actual ratings that will be used by the modeler and by the front end. So the modeler will consume data from the data store, and the front end will also consume other relevant information, such as usernames to make profiles or relevant movie names to build the web pages. And the model store will just consume data from the data store. So the other storage component, which is quite important, is the actual model store. So the main role for the model store is to actually store the serialized Spark ALS models. And the way the model store is consumed, so in this case, the modeler, after training, will serialize the ALS models to the model store, and the predictor will then just fetch a model from the model store and use it to perform the predictions. So the models are serialized, and they're serialized. They can be accessed by the predictor in several ways. So it can be accessed by ID. So that will be useful if you want to load two different distinct models, so we can compare them in an A/B setting, for instance. Or you can just load them by timestamp. So the predictor could be constantly asking for the latest model, so it has also always a fresh version of the models for predictions. And we use a MongoDB for no particular reason. We could have chosen any backend, specifically because these were implemented with backend agnostic ways. So we just wrote like a general abstraction for writing and reading models, and the specific backend bits can be implemented from any other storage engine. So next, we look at the Predictor service. So the Predictor service is basically a REST web server, and it's implemented as a Flask application in Python. And it is responsible to give the predictions given our model, given the current ALS model. And we basically perform two types of predictions with this predictor. So we do ad hoc user product pair predictions. So we can just request what are the ratings for this product and what rating will this user give to this product, and just give a list. Or you can do top K predictions. So you can just ask, what are the best products for this user? What is the stuff that he's going to like? Or we can ask reversely, which users are the best suited for this product? So which users are more likely to like this product? And the predictor store then connects to the model store to fetch the models and stores the predictions in a cache store if they're not present at the cache store. So the modeler can only produce so many models at any given time. So it's not going to be constantly predicting models, especially with a full data set, which is 26 million ratings. So it takes a little bit to produce a model. Not very much, but let's say 2 minutes to produce a model. So in that case, it doesn't make sense for the predictor to be constantly asking for new models. So we have some rate limiting on the predictor, and we can just configure that and say, well, just ask for a new model every 2 minutes if you want. So that will really help with performance, especially if you're asking for a new model every time there's a web request on the REST server. And also, for the predictor service, we have this characteristic where the model is returned, is serialized, as I mentioned, and is returned as an array of a multi-dimensional array with some relevant metadata for that model. And that data is going to be instantiated into a Spark ALS model. And that's one of the first problems that we found, because the actual Spark ALS implementation stores the models as a matrix factorization model class. And that takes basically the wrapper around to RDDs, so an RDD of an int and an array of doubles. And the problem is that these are Scala typed. And as I mentioned, the predictor was implemented in Python, sorry. So we will have access to the PySpark framework. And it's really tricky to implement these Scala types in Python. So, all right, okay, out of time.
Should we just do our conclusions?
So, okay, just so really quickly, I'm really sorry for this, guys. So, do you want to do Sophie?
Yeah, should we just put our conclusions up? Press the button. Okay, so Spark has what you need if you want to go home and implement this. You can also find all of our code on the GitHub RAD Analytics repo, and that's within the Jiminy project. So please take a look. There's huge advantages of splitting your system into microservices. And yeah, easy to deploy on OpenShift. So yeah, thanks for your time.
Okay, so if anyone has any question, please make. Yeah, so it's really completely out of time, no time for questions even. Okay. All right, so if anyone has any questions, we can just